So, interestingly enough, this is the February issue of the American Math Monthly Journal. And one of the notes in here is titled "The Possible Asylum." Now, you might read that and go, what the hell is the asylum story doing in a math journal? But it turns out the possible asylum is a discussion about the satisfiability of one of Raymond Smullyan's problems. Remember our knights and knaves guy? He wrote a whole bunch more, and one of them is about a set of asylums. The last asylum Craig visited was the most bizarre. The asylum was run by two doctors, Dr. Tarr and Professor Feather. There were other doctors on the staff. An inhabitant was peculiar if he believed he was a patient. An inhabitant was special if all patients believed he was peculiar and no doctor believed he was peculiar. Inspector Craig followed the following conditions. Are these propositions satisfiable? Well, it turned out, depending on the way you translated English to geek, we thought the answer was no. For a very long time, this was referred to as the impossible asylum, because there was no way to satisfy these conditions. Here's an alternate reading, translating this from English to geek slightly differently, that turns out to be satisfiable. So our satisfiability of axioms, satisfiability of propositions is still being done as research today. Anyhow, you should have homework for me. Let me come around and get it. Then we'll talk about arguments. In a sense, it is worthwhile, if you have that sort of peculiar sense of humor, to go watch the Monty Python argument sketch after we finish today. So, what's an argument? The real question. What do we mean when we say we have an argument?
I think an argument is either for or against a statement. It's evidence for or against a statement.
In one sense, yes. In another sense, an argument is a disagreement, right? In formal logic, an argument is a series of propositions and rules applied to those propositions that leads to a conclusion in support of or against some idea, right? So I'm going to actually write our logical definition of an argument. It's a sequence of statements that end in a conclusion. And one of the questions is, well, what makes an argument work or not? Rather than talk about the truth or falsity, because that's about propositions, I'm going to talk about the way in which an argument is structured. An argument is valid if the truth of the conclusion, one of the propositions, follows from the truth of all the statements in front of it. in this sort of logical format, I'm going to refer to these statements as premises, a premise. And I want to say, hey, if we accept that all of these premises are true, then my conclusion must be true. In other words, I want something like this. I don't want it to be T arrow F, because that would make the whole thing false, right? That's our if-then setup, where these are our premises and our conclusion is here. But this is not telling me what the actual propositions are. This is a form of an argument. So really, if I had a bunch of premises, however many of them there are, I want to show that this sentence is a tautology. Wait a minute, I know how to do that, right? I can build a giant truth table. I know how to do that. Problem. Every time I add another proposition, what happens to the number of rows in my truth table? 4, 5, 6 propositions. I'm looking at a hell of a truth table, aren't I? Then I got to do a giant and statement. Some of these individual premises may be not single things, they may be compound things. So this could get really ugly really quick. Big truth tables, lots of propositions, not a good idea. So instead of trying to do this, what we want to do is we want to look at the form of an argument and decide if that form is valid. But any argument that's not valid is, I know this word in English, invalid. Normally, an invalid argument is called a fallacy. And in formal logic, there are a very couple of particular fallacies. In normal oratory and rhetoric, there are lots of fallacies. The Wikipedia page for fallacies has something on the order of 100 entries. It's not small. But those are argument devices in speech that you'll hear frequently. Straw man arguments, red herrings, non sequitur, which literally means it doesn't follow. We can talk about all these ideas. But we need to start with what forms are valid. So let me start with one of the first ones. The law of detachment, also referred to as modus ponens. I'm perfectly fine just calling it detachment from here on out, but you'll see the Latin phrases often. This is, again, a classical formula out of philosophy. And the original example comes from either Aristotle or Plato. Now, quite often when we write a form of an argument in logic terms, we stack the premises. So another way to write this same sentence is to write this. And then we write, therefore, we have a conclusion. Those 3 dots and a little triangle. That's the logic symbol for therefore. So this argument, modus ponens, I think this is true. This form should be valid. Well, how do we tell if this form is valid? This one's small enough. I should be able to do it directly. There are only two propositional variables. There aren't that many different hypotheses involved, not a lot of premises. So let's actually do this one from scratch. Let's make the truth table for this. Go for it. As some of you will see in the homework that I handed back, I would like you to be very clear as to what is a T and what is an F. In a couple of places on some people, I saw things that looked like this. I couldn't tell what it was. So please don't do that. Okay. I want to set up this sentence. So I'm going to do the if then. What's the truth values on my conditional? And then I just copy down P again. That's an optional sentence. You don't actually have to do the copy if you don't want to. We're going to AND those together. What happens there? Now I want to do this. Arrow Q. This time I didn't copy it down. I can just do this. So what happens? Hang on. If the antecedent is false, this would be F arrow F. What's F arrow anything? That's our true, right? So all three of these are true because the antecedent was true. If this is T arrow F, we have a problem, but it's T arrow T. It's true as well. This is a tautology. And that means that any argument of this form is valid. It's logically correct to say this sort of a thing. Yes, sir.
Why is false anything true?
I got to go back to our original truth table for the arrow. We originally decided this was going to be true, this was going to be false, right? Now, if I make both of those false underneath there, then this truth table is exactly the same as the AND table, TFFF. And I made this argument that this should be like a slide, right? If you go up the slide and you can slide down, if I go up and I got to the bottom, the slide is working. So I go up the ladder, I get to the bottom. I went up the ladder, I got to the bottom. Okay, and that's why I said, hey, I never went up the ladder. I could still get to the bottom, couldn't I? There we go. 3 sentences. If it is raining, then the pool will be closed. It is raining. The pool is closed. Make sense? Or am I talking out my ass? That's exactly this argument. If it is raining, then the pool will be closed. And it is raining, then the pool must be closed. Okay, I get it. I like this. I am in a windowless room. If it is raining, the pool is closed. I call the pool, yeah, we're closed. What do I know? Aha. Why do I know that? But that's because the argument is valid. I know that this sentence means the same thing as this sentence. So here's a problem. I call them, they tell me they're closed. Was that this? Okay, I have a problem here. Why else could the pool be closed? Why not just be raining?
They needed to do maintenance.
We got to paint the bottom of the pool. We needed to adjust the chlorine levels. We didn't have a lifeguard on duty today. We couldn't open the pool. So that's not a problem. We just made a mistake. We said, instead of doing it this way, we want to do it this way. Do those mean the same thing? What did we say was the relationship between these sentences? If this is the original, what do we call this one? The converse. So what we just made is a converse error. That's a fallacy. Now, again, I would ask, how do you know it's a fallacy? Because what I would be doing is trying to show this statement. Oh, no, sorry, not there are no knots here. Try again. If it is raining, then the pool is closed. The pool is closed, it must be raining, right? I claim this is wrong. Let's check. Let's see if this is wrong. I'm going to do the same thing. I'm going to make my truth table. I'll make them P and Q in the same order. See, even I do it, I'm writing too fast. P arrow Q. True, false, true, true. Now, P arrow Q and Q. What's that and column look like? Well, I can avoid this. So it's false in which rows? The last one and the second one. But it's true here and it's true here. Now, this whole thing, arrow, P. I'm good. I'm good. It's the arrow's going this way from here to there. That's not going to work. In order for this to be a valid argument, the result has to be a tautology. Now, I called this a converse error. The textbook calls it the affirming of the conclusion. I beg your pardon? Oh, wait a minute. Hypothesis conclusion, right? Hypothesis, conclusion. Isn't that what we called these pieces as well? Hypothesis and conclusion. So if I use this as my reason, not as my answer, then I've affirmed, hey, no, I'm going to tell you that this part is true. I've affirmed the conclusion. That's the wrong way around. I am much happier calling it a converse error because I see that I went the wrong way on the arrow. Questions? Come on, talk to me. Same room. The windowless room. If it is raining, then the pool is closed. Call the pool. No, we're open. What do I know? It's not raining. Does that work? Why?
Because if it was raining, then it was.
And that is this equivalence, isn't it? If it is raining, then the pool is closed. If it is not raining, then the pool is not closed. Those are the same. Now, that's the same idea as detachment, just the other way around, right? So they gave it another name. Again, I didn't come up with these names. These are 2,500 years old. I didn't make them. They call that modus tollens. I hate this word. I'm going to call it detachment of the contrapositive. Contrapositive, because that's what we used right here. The contrapositive. That's our detachment. Again, we use the same idea, but we have a not Q and not P, and that works. Memorizing all this stuff is going to take a long time. Working our way through all the arguments is going to be a pain in the neck. Turn to page 76. Pencil. Like I said, I call that first one detachment. I call the second one contrapositive detachment. But those are the formal names in logic, modus ponens and modus tollens. Let's look at the third one. What the hell's the third one say? Just go over here and let's see if we can read this part. This setup. This setup says, if P then Q, if Q then R. Therefore, if P, then R. Like a line of dominoes, right? If P then Q, if Q happens, then R happens, and boom, if I started, it ends. Okay, wait a minute. From A to B, from B to C means from A to C. I've seen that before. If A is less than B, and B is less than C, then A is less than C. We call that the transitive problem. I'll call this transitive. The official name is the hypothetical syllogism. Forget it. Just stop right there. No. Nope. P or Q, but not P. What do you get? You better get Q. If I have P, then I could easily say I have P or Q, right? Because when you add stuff on, the truth value from P is maintained. And or is true if either one is true. So if P is true, then P or Q is true. P and Q. And is only true when both are true, right? So P and Q, therefore P. Both of them have to be true. So at least this one is true. If you are a math and computer science major, then you are a computer science major. If I have P and I have Q, then I have P and Q. I hope that one actually sounds as dumb to you as it does to me. And then way down here at the bottom, P or Q, not P or R. Therefore, Q or R. Why does that work? I mean, I could make the truth table, but I think that's more of a pain in the ass than it's worth. Roman?
So. Have P, then. You don't even have to worry about Q, but then if you don't have P, then you have R.
Aha, but if I have P, then I don't have not P. So out of this two, one of them must be true. You just said P was true. Out of this two, one of them must be true, but P is now true, so not P is false. That means R has to be true. The other way around, if P is false, for this first sentence to be true, I have to have Q. But then I don't have to worry about this one at all. So it's either Q or it's R, because one of P or not P should be true. Talk to me.
So they just cancel each other out and you can just take the other two.
In one sense, cancel, yes, but I don't want to use that phrase because we did canceling as part of our factoring idea with the distributive rules. And I really don't like using that phrase in a different place like that. Again, I don't expect you to memorize these. Put a post-it flag on this page of the book. If you've got the PDF, put a tab on this. This is, again, something that I think you will need regularly. That's the hint dropping again. Questions? 1, 2, 3. Yes, sir. Oh, no. In the same vein as when we started using the tables on page 27, 28 to simplify our propositions, knowing the names is nice. If you want to write down the reason next to each one, knowing why you write each line of the argument, it would be important to get that the first couple times, but do it with the table in front of you. I don't want you to memorize any of that. But seriously, use whichever versions of the names you want. You'll notice in the last couple, I didn't even name them. I just need to know how to build an argument. And that's what I want to do next.
When we start making our equation tables for the quizzes, are we able to just copy this entire thing and put it on a piece of paper?
Please note that the statement for my formula sheets is as follows. You are entitled to one side of 1 8.5 by 11 handwritten sheet. 8.5 by 11 inches, a standard piece of notebook page. Or printer paper if you want to use that, but make sure the other side is blank, not something else. I'm recycling, you should. One side. One side of one. The only thing on the back of it should be your name. That way, if I drop it by stupidness, I can get it back to you. All right. In a lot of cases, our goal is to understand from a group of sentences what valid arguments we can make. So, on page 82, problem number 5 reads as follows. Here are some hypotheses. Randy works hard. If Randy works hard, then he is a dull boy. All work and no play makes Jack a dull boy. The Shining. Go watch the movie. If Randy is a dull boy, then he will not get the job. Is the following conclusion valid? Randy will not get the job. Let me copy this down. So, again, I've got several sentences here, several propositional variables. The first thing it says is Randy works hard. So let's give that a letter. The second sentence says, if Randy works hard, then he is a dull boy. Well, there's another propositional variable, right? There's an if then there. If Randy works hard, then he is a dull boy. So I will write down Q. The third sentence says, if Randy is a dull boy, if Q, then he will not get the job. And now I can read off the hypotheses they gave me. The hypothesis they gave me in the problem started with Randy works hard and if Randy works hard, then Randy is a dull boy. And if Randy is a dull boy, then Randy will not get the job. And my conclusion is Randy will not get the job. Is this valid? Regardless of whether it's true or false, is it valid? Now, here's the problem. A bunch of you are nodding, a bunch of you are going, yes, a bunch of you are going, of course it is. Why do you know that? Emily, talk to me. The silly one, hypothetical syllogism, it's silly, I get that.
Yeah,
Transitive.
translate, it's like a domino effect. So if one happens, it goes to the next, which goes to the next, which concludes.
So let me do this. I'm going to number these. Right? And what you just told me to do is use that hypothetical syllogism, that transitive property, on 2 and 3. If I do that, what is the valid conclusion from that sentence? If P, then R. And I know this is valid. And that means that now I could use this sentence instead of 2 and 3. Right? Because we just built a new valid thing from our statements. So I'll take that and number 1, put them together. What rule am I using when I put those two together? My detachment rule, modus ponens. So I can say, yes, this is a valid conclusion to have. As opposed to our idea, I called the pool, they're closed, so it must be raining. That was an invalid conclusion. Valid argument versus an invalid argument. Regardless of whether or not dull people get jobs, that's not relevant here. Whether it's true or false isn't as important in this part of the setup. Questions? Talk to me. We had a converse error. That was the one we did with the, what was the other piece? We have contrapositive, we have converse, what was the other one? And what was the difference between the original and the inverse? So, if it is not raining, then the pool is not closed. Right? So if I go and I look outside, hey, it's not raining, I can go to the pool, right? But that's not logically equivalent to my original sentence. Because again, as we said before, there are other reasons that the pool might be closed. So that's again another fallacy. An inverse error, just like a converse error, because those two are not actually equivalent logically. If you study hard, then you will pass the exam. Is not the same thing as if you don't study, then you won't pass. Maybe you've taken this course already, you know all this formal logic because you took a logic course before, and you're good at this graph, and you don't even study this first chapter. You're going to waltz through this part. Maybe. I don't know. That last one that we were talking about with the P or R, not P or not Q, that one. This one down here, resolution, was the last one in the list. If you don't have anything that's an if-then, if everything's written an and or a not, this allows you to do a lot of simplifying. And that's helpful. So we refer to a set of propositions that do only contain and, or, and not. We call those clauses. And those sorts of clause resolutions are what is best used here. So the two primary fallacies in this text are a converse error and an inverse error. Affirming the consequence or denying the hypothesis. I'm perfectly happy calling them inverse and converse, but it's important to know which way we're going when we look at modus ponens and modus tollens. But everything in this problem that we just did was about Randy. Do you know Randy? Me neither. The original sentence that was used to describe modus ponens is absolutely general. And this sort of generalization comes from the idea of using a quantifier. What is a valid conclusion from this? Bingo. But what I've done here isn't really modus ponens. Because what is that first sentence? It's not an if-then, is it? You might want to think of it as an if-then, right? If you are a man, then you are mortal. Socrates is a man, but that's not the same way we wrote the previous sentences, are they, right? If Randy is dull, then he will not get the job. That was specific. What we've gone from here is from a universal statement to an example. All men are mortal. Socrates. Algebra class. I know it's math class underneath it. It doesn't sound like it so far today. It's a math class underneath it. First thing we learned in algebra class is I wasn't going to use a number. I was going to show something that was true for this thing we don't know. Or we're going to talk about properties for all kinds of numbers, right? And we used a variable. And then eventually we go back and say, oh, no, if you want this to be true, then x has to be 3. First question, why do we use x? Do we know why we use x? I wish it were, but originally, a lot of the books for algebra, the word itself, al-yabar, the method of reduction and completion, is the title of a book by an Arab gentleman. He didn't write in English. So why did we use x? Arabs didn't. The original algebra book uses the word thing. Find the thing. The thing that does this. Find the thing that we're looking for here. When those Arabic books were translated to Italian during the Renaissance, they were written in Latin. In Latin, the thing, or in Italian, the thing, is c'è cosa. C'è, the, cosa, thing. The school that taught algebra was called the Casas school, the thing school. Go to the thingy school, figure it out. C'è cosa. In Italian, Che doesn't have a letter. If we're writing in Latin, che is written chi epsilon. It's an X. It's a great story, isn't it? I have no idea if it's true. The other version is that those books were written in Arabic. At the time, Spaniards, the Moorish, were Arabs. They were Islamic. Spain and Portugal were Islamic countries during that time of the Turkish Empire. And shy thing would start with a letter, but there is no sh sound in Spanish. In Spanish, right? Go through the
German.
but you said you could say that word in Spanish. If you took Spanish, go through the language, think about the sounds you make in Spanish. Sh isn't in there. So how do you say shy? Which is the Arabic word for thing. You can't. They stole an unused letter in the Spanish alphabet. Because in Spanish, how do you pronounce an X? You don't. Javier. It sounded with a J. They write it with a J. They don't write X. It's an unused letter, so they figured they'd use it. I don't know which of these stories is true. History is weird. So, this idea that I went from a variable, all men are mortal, to a particular example is called universal instantiation. Any fans of the Matrix movie? Star Trek fans? What was interesting about 7 of 9? Right? She was a rescue from aboard. In the Matrix movies, they talk about you are the 6th instance of this, right? The end of whatever the 3rd movie was, where he confronts the architect. Revolution. I forgot which movie is which. You're the 6th time this has happened. You're an instance of a more general pattern. We do this in math all the time. I want to show something is true for a number. Which number should I use? I don't know. Let's call it X. We'll get to figure out what it is later. Here's the number I want to use. What am I going to call it? Fred. All men are mortal. Pick one. Socrates. He must be mortal. In a general statement, I would write, for all X, some property is true. And then I would say, oh, if I pick one, that must be true. But this is a universal statement. So here's my instance for this universal thing. I gave it a name. The other way to do it is the way we were just talking about, existential quantification. There's some X for which P of X is true. There is a number that has the following properties. It is the sum of its proper divisors. The numbers that divide into it add up to it. Like 6. The numbers that divide into it are 1 and 2 and 3. Add those up, you get 6. 28. It's another number that has that same property. But I can say, okay, there is such a number that does this. Therefore, I'm going to give that number a name. And now, whenever I want to talk about this number A, you know it has that property. This is existential instantiation. So I went from There's this property that's true. Here it is. Here's the thing that has this property. We'll use it. There might be more than one, but here's one. We'll call it A, and off we go. And go the other way around. If you were to tell me there's a number with this property, then my conclusion can be there exists X so that this property is true. In other words, instead of saying, I have a rule, here's an example where I have an instance, I can say, here's an instance. I must have a rule. I generalized instead of instantiated. So this is existential generalization. And in the same vein, what's the conclusion that goes with this one? Almost. For every X, P of X. A universal generalization. Existential and universal. Again, I can combine these with my other rules. So I can have universal modus ponens or universal hypothetical syllogism. I can work my way through these things. Why would I do such a thing? Because I'm a sick, twisted bastard. But that's a separate reason. Most of the time, I would do this thing so I can make a valid conclusion or a valid rule from definitions in whatever field I'm talking about. In programming, I do this sort of thing. So, hey, these are satisfiable. This is going to run. This is the operation behind a debugger. In addition, all of formal logic applies to every field of study, which means you should start with a set of things, a set of hypotheses you know to be true, and then deduce from them conclusions that you can make valid arguments from. In a very real sense, this was the Greek contribution to math and science. What they said is, we're going to follow these sorts of rules about thinking, and now we're going to apply them to science, to math, to geometry, to music. The reason the notes we have sounding nice is because they're nice fractions of the lengths of a string. In a very real sense, all of this comes down to the way in which we apply the rules of logic. On our Canvas page, I put up an article I received again in another journal just a couple months ago. This article is called The Art of Formal Proof. All of the ways we've hung these sentences and propositions and things together can be turned into creed. And the pictures you get out are really interesting. You should read that before our next class. It's only 3 pages. It's not very long. But speaking of that next class, when is our next class? If you look at our calendar, no, our next class is Monday. We don't have class Friday because there is a middle school math competition. It says on our calendar, math counts. I'm leading that group here on campus. I have to be there. They're running till 1 o'clock. I'm not going to start class, I'll only go for 20 minutes. So we don't have class on Friday. That means your next homework is due on Monday. I will see you all then. Have a wonderful weekend. But please note, also, you should all have gotten an email about the weekly study groups that start Wednesday next.